Okay, today's lesson is going to be on an introduction to polynomial functions. Basically, what I'm going to want to do for the first part of this unit is have you look at the equation of a polynomial function, and just by looking at the equation, I want you to be able to pull out certain characteristics of its graph. And today we're going to look at some of those really important characteristics, and then we're going to really focus in on just one of them. So before we get started, I guess we should kind of define what a polynomial function is. And a polynomial function is any function that is written where your variable of x, your domain, is raised to a natural number. Now remember, the natural numbers are the counting numbers, so they're not fractions, they're not negatives, starting with 1. So 1, 2, 3, 4, 5, 6. And of course they can be in a whole string of terms. So for example, let's just take a look at some examples of polynomial functions like this. Y equals x cubed. Notice the exponent 3 is a natural number. Minus 2x squared. Again, this is a natural number. Plus 5x. Now the exponent for x here is a 1. You don't see it, but it's a natural number. Minus 7, a constant. This example here we call a cubic, based on the highest power of x is a cube. Here's another example. F of x equals 2x to the 7th minus 3x to the 4th plus x. Again, every power of x is a natural number. Even this, y equals x, our basic linear function. This counts as a polynomial function. The power of x is 1, and 1 is a natural number. And sometimes it helps to look at non-examples. These are things that are not polynomial functions, such as y equals the square root of x. Remember, if we rewrite this using exponents instead of the square root symbol, it would be y equals x to the 1/2 power. And again, that number, that exponent 1/2, is not a natural number, so this would not be a polynomial function. Another non-example would be this, because we could rewrite, of course, we could rewrite this expression right here using 5 times x to the, using negative exponents, negative 3rd power. Remember, a negative exponent flips a base. And negative 3 is not a natural number, so this would not be a polynomial function. So let's dive into polynomial functions, and you can follow along in your guided notes. And let's take a look here at this particular polynomial function right here. There are several characteristics we really want to hone in on polynomial functions, things that are always going to be true for polynomial functions. The first is, if you have a polynomial function, it is continuous. And that might be a new word to some of you, so let's break that word down. Continuous means the graph of the function is unbroken. You could trace the entire graph without lifting your pencil once. So let's take a look at a couple graphs. We'll just take a little side trip here and take a look at some graphs and decide, hey, are these graphs continuous or not? So the first graph right here, you can see it's finite on one side. It stops right here. But sure, I could take my pencil and I could trace the entire graph forever without lifting the pencil up. So this first graph, yes, it is continuous. Now let's go right here. Here's a graph. It's all wavy, and that's fine. I'm trying to trace the whole graph, but right here we have what's known as a hole in the graph. That at this point, it looks like the point 1, 1, there's a hole. And that would make this graph not continuous. Because it has a hole, there is a type of discontinuity to this graph. So I'd have to lift my pencil up to get to the other side of the graph. Down here we have a graph that's, you can see it's broken up into 2 pieces. This graph is not continuous. You can see, to go from this part of the graph up here, I'd have to jump. My pencil would have to lift off the paper, and I'd have to jump up to get to this. And we've actually seen this type of graph before in our piecewise functions. So this is not a continuous graph. And down here you can see this blue dotted line. Remember, that's an asymptote and it's ripping this graph up. It is not continuous because I can trace the left side, but to get to the right side I have to lift my pencil up and go to the right side because of that asymptote. So nope, this is not continuous. So let's go back and look at some other characteristics of polynomial functions. The domain is negative infinity to infinity. The domain, the x values, this graph goes on forever to the left and on forever to the right. The domain, the x values, are infinite, to the left, to the right. Roots are very significant in this graph. The roots, and we've seen that word roots before when we're talking about parabolas. The roots, where the graph crosses the x-axis, you can see that I have roots. I have 4 roots here in this graph. Those points where the graph crosses the x-axis, roots are also called x-intercepts. They're also called zeros. And if you think about why they might be called zeros, think about the coordinates of all 4 of these roots. What do all 4 of these coordinates have in common? Well, they all have a y value that's 0. So that's why we call roots zeros. What else? Well, there's something else in roots that we want to hit on, and that's this idea of a double root. A double root is seen graphically by when the graph bounces off the x-axis. And you can see right here we have this double root where the graph bounces off the x-axis. We'll see what that looks like when we represent this function algebraically instead of graphically. But graphically, you know you have a double root when the graph bounces on the x-axis. The y-intercept is very significant. You can see this graph has a y-intercept right here at the point 0, 4. Notice it's singular, not plural. We cannot have multiple y-intercepts because if we did, well, it wouldn't be a function. We really want to focus on end behavior. And end behavior is what your graph is doing at the ends. At the left end, this graph is going down forever. At the right end, this graph is going up forever. And finally, there's one more component we're going to just focus on, and that's relative maximum and relative minimum values. Now, relative means relative to the space around. So you'll notice this little hill here. This point at the top of the hill is a relative maximum value. It's not the maximum value of the graph. It's not the highest point of the graph, but it is relative to the points around it. And this hill is a relative max. And this valley down here, that's a relative minimum. It's not the lowest value. This graph goes down to negative infinity. But relative to the points around it, it's a minimum. And then this double root is also a relative minimum. So let's take a look at what we can discover on our own. What I'd like you to do is to open your computer up to Desmos, and I want you to do problems 1 and 2. And 1 and 2, these are the important things I want you to fill out. What's the end behavior of your graph? What are the coordinates of the roots? And what's the y-intercept? So this would be a really good time to pause your video, try number 1, and then when you're done with number 1, unpause the video and we'll talk about it before you do number 2. Hey, welcome back. I hope you made a fairly rough sketch. Doesn't have to be 100% accurate, but we are going to do a sketch of this shape. Hopefully, before you sketched it, you realized it was a parabola, and it looks something like this. And, oh, whoops, that's supposed to be an arrow. And again, this is just a very, very rough sketch. We don't need it to be exact here. But let's focus on what we've got going on here, the end behavior. This says, and it's nice for me to read it out loud so we can see what the symbols mean. As x approaches, that arrow means approaches, negative infinity. As x heads towards negative infinity. So as I'm on this graph and as I am heading to the left, remember x heading to negative infinity means we're heading to the left. What is my y doing? Where is my y headed? Well, as I head to the left of this graph, my y is headed up. And then this end behavior, as x goes towards positive infinity, as x approaches positive infinity. So as x is moving to the right, as I move along this graph to the right, what's my y value doing? Well, it's going up. The roots where you cross the x-axis, you can see in your Desmos graph that those roots are at negative 4, 0 and at 2, 0. And the y-intercept is at the point 0, negative 8. So now is a good time to pause as you try problem number 2. So why don't you pause the video, try number 2, and then come back. Hey, welcome back to problem number 2. Let's see what you did. Hopefully when you graphed this problem, you graphed it as doing something like this. It comes up here, and then it goes down, and then it shoots back up again, like that. And so when we look at things like end behavior as x approaches negative infinity, meaning as we move along this graph to the left, the y seems to be going down. As x approaches positive infinity, as x goes to the right, the y values seem to be going up. They end going up. The end of this graph starts down, goes up. Roots, you can check Desmos and find those 3 roots, and there is your y-intercept at 0, 2. And just a quick word, because some of you might be thinking this already, and if you are, that's awesome. Remember, we call roots zeros, and we call them zeros because these roots, these 3 points here, are where the graph crosses the x-axis. And that means the y value would be 0. Well, if I set y to 0 and I solved this equation, look at the answers you'd get. You would get x equals 1. And notice I had a root at 1, 0. Here you'd get x equals negative 1. And notice I had a root at negative 1, 0. And finally, when we let y be 0 and we solve, we get x equals 2. And sure enough, look at this. We had a root at 2, 0. As a matter of fact, over here, we could do the same thing for these roots. We didn't need to graph it. We know roots are called zeros because the y value is 0. And if I wanted to solve this equation, well, I'd probably factor it. Let's see what this factors into. What's the quantity of x plus 4 times the quantity of x minus 2. And if I solve this and I set this equal to 0, I'd get x is negative 4. And notice negative 4, 0 is a root. I'd get x equals 2. And notice 2 is a root. So one thing we kind of noticed right away is that roots are called zeros because the y value is 0. And if we can factor, or if we have an equation that's factored already, finding the roots is kind of easy. But what I really want to focus on now is the end behavior. So what I'm going to ask you to do is turn your notes over, and you've got a series of graphs I want you just to sketch. So to focus on end behavior, I just really want us to sketch the graph. So when you're drawing these, just a rough sketch will do. Like if you look at problem 1 on the back, I just want just a general rough sketch of what this thing looks like. It kind of goes like this. But I really want you to make sure that we're looking at the end behavior. What's happening at the end of this graph? When you're all done with this, we'll come back in person and we'll talk about what we discovered. Good luck.